Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about linear free energy relationship. So this topic also very important for master students. You know friends, I will discuss here from the beginning. Two types of experiments were considered for the investigation of organic reaction mechanism. First one, kinetic studies, and second one, thermodynamics studies. How fast and how far? So in-depth analysis of a structure of transition state or reaction mechanism is obtained from studies of effect of substituents. A substituent effect is the manner in which the reactivity of the molecule changes when substituents are changed. My friend, organic compounds uniquely are capable of structural variation in the vicinity of the reaction center, permitting an almost continuous variations in its electrophilic or nucleophilic character. This capacity may be used as electronic effect of a structure upon the reaction's affinity, and from which electronic demand of the reactions may be inferred. So, we will focus on these two important points. So, in order to investigate the mechanism of reaction using substituents effects, we are to study with different reactant in which a substituent has been changed, and to see how this changes the reactivity functions of the molecule. These substituents effects are used to determine how the free energy of reactions and activation energy vary as a function of chemical structure. And these substituents effects are referred to as structure reactivity relations. This structure reactivity relationship is often very informative about the mechanism of the reaction. Use of this information in deductions of organic reaction mechanism is a highly developed art applicable to polar reactions in particular. So my friend, electronic demand of chemical reaction, supply of electron to the nucleophilic center, and the withdrawal of electrons from the electrophilic center. So you can see the electron donating situation and electron withdrawing situation. So experiments can be designed to test change in electronic nature of reaction center along the reactions coordinate by switching an electron donating group to electron withdrawing group. A positive charge is being created in the transition state of rate limiting steps, then adjacent electron donating electrons should stabilize the transition state and the reaction should speed up. Conversely, adjacent withdrawal groups also destabilize the transition state and therefore retard the reaction. Opposite effect should be observed if negative charge is being created in the transition state of rate determining steps. Now, suppose it is desired to investigate the electronic demand of ester hydrolysis by aqueous alkali to identify the nucleophilic and electrophilic centers and the degree to which ester respond to substituent change. So you can see the substituent X, NO2, CN, chloride, H, methyl, OM. Rate constant you can see are different. So empirical correlations given by the Hammett plot. The influence of function group on the course of reaction shows uniform pattern which is qualitative in nature. For quantification of this pattern, empirical correlation has been useful. The development of means by which one body of data can be related to another is called empirical correlations. Empirical correlation of reactivities of organic compound are often linear relationship involving logarithms of rate constant K and equilibrium constant K. So you can see the substituents and log K value, electron withdrawing and electron donating. So this is the empirical correlation Hammett plot. You can see the electron donating and then electron withdrawing and between neutrons. So there is a relationship log K is equal to rho log K plus C. So linear free energy relationship, the Hammett equations. The Hammett relationship only applies to the system where the substituents are attached to the reaction center via aromatic ring and the situations meta or para. Ortho-substituted aromatic ring do not fall on the line owing to a steric and through a space effect, that is increased crowding in the tetrahedral intermediate. Aliphatic acid do not fall on the line due to a small increase in steric crowding in the transition state, and their increased flexibility may decrease correlations between the transition state in structure and equilibrium positions. So, in 1937, Hermit recognized that electronic influence of substituent X on the reaction center Y may be assessed by studying reactions in meta and para substituent of benzene derivative. You can see here the situations. Quantitatively, this electronic effect of each substituent related to hydrogen may be obtained by comparison of del G for dissociation constant of substituent benzoic acid with that of benzoic acid. Therefore, substituent effect is equal to minus Gx plus del Gh is equal to log Kx minus log Kh is equal to log Kx by log Kh is equal to sigma x, where sigma x substituent constant, thus electron withdrawing groups are therefore characterized by positive value of sigma x and electron donating groups are characterized by negative value of sigma x. And this magnitude is the measure of these quantities. So you can see the log K and log sigma x value, negative and positive. So the substitution constant sigma for meta and para substituent benzene deviate as defined on the basis of ionization constant of substituent benzoic acid in water at 25 degrees Celsius, that is X is equal to S. Sigma is collective measure of total electronic effect of a substituent. Resonance and inductive effect is now how electron withdrawing or donating substituent is its stability to supply withdraw electrons to or from the reaction center. So sigma is independent of nature of the reaction site. Sigma is defined separately. Sigma m for meta substituent, sigma p for para substituent. Inductive effect caused by polarization of sigma bond, sigma am greater than sigma p for given substituent due to its closer proximity to the reaction site. Resonance effect conjugate is stronger for para substituents than meta, sigma p greater than sigma m for a given substituent. So strong conjugation into carbonyls, conjugation into ring not carbonyl, valence weak effect of X. You can see in this book. Now, the plot of logarithm of rate constant against the corresponding sigma values of the substituent results a straight line passing through the origin. The slope of a straight line is termed rho, which is called reaction constant. So, using the equation y is equal to mx plus c, we have log kx plus rho log kx plus c for substituent aromatic ring, equation 1. Log h is equal to rho log h plus c for unsubstituted aromatic ring. So where k rate constant for the steady reactions and capital K equilibrium constant for benzoic acid dissolution. Now subtracting 2 from 1, we get log kx minus log kh, rho log kx minus rho log kh, or log kx divided by kh is equal to rho log kx by kh is equal to rho sigma x. So equation 3 is known as Hammett equation. If you plot log kx by kh against sigma x, the straight line will pass through the origin. So, why is Hammett equation considered as a linear free energy relationship? LFER. The straight line relationship between log K for the reactions of ester and log K for ionization in water of corresponding carboxylic acid implies there is a relationship between del G, the free energy of activation for the ester reactions, and standard free energy, the standard free energy change of ionization in water of this. The straight line correlations between the free energy term for two different reactions are referred to as a linear free energy relations. The rate constant and equilibrium constant are related to the free energy difference by the equation. So log K is equal to minus del G standard del G divided by 2.303 RT, and log K is equal to standard del G 2.303 RT plus log K prime T by H. K Boltzmann constant, H Planck constant. So now the Hammett equation may be written as multiplying both sides by 2.303 RT, and then you will get the final this equation. There are linear relationship called linear free energy relationship between the activation energy induced by the substituents and a parameter that describes the electron donating or electron withdrawing characteristic of the substituents. So friends, the substitution constant sigma x can be defined as log kx minus log kh is equal to log kx divided by kh is equal to sigma x. You can see the sigma p and sigma m if substituents occur. So for h 0, 0. This value remain constant for a specific substituents in a specific position irrespective of nature of the particular reaction. So an electron withdrawing group has a positive value of sigma and electron withdrawing group has negative value of sigma. So electron withdrawing positive and electron donating negative. Now reaction constant sigma and its rho and its significance. The slope of Hammett plot of log kx divided by k versus rho is versus sigma is rho, the reaction cost. This is measure of efficiency with which various substituents transmit their electronic effect to the reaction center. The value of rho for a particular reactions carried out under a specific condition remain constant no matter what the meta or para substituent present in compound state. So sign of rho positive, electron withdrawing, negative, electron donating. When sigma greater than 1, reaction is more sensitive to substituents effect than benzoic acid, and negative charge is building in the transition state of RDS. When rho less than 1, the reaction is less sensitive to substituent effect than benzoic acid, and negative charge is still building in the transition state. And when rho is equal to 1, the reaction shows no substituent effect, no changes in charge occurs in the transition state of RDS. When rho is negative, the reaction is creating negative charge in the transition state of RDS, rate determining state. So my friends, I will show you examples in our next video. So if you like this video, then subscribe my channel, and thanks for watching. And also you can share in your circle.